Okay, so in the previous video, we talked about phasors and average current. Phasors and average current. Now we are going to talk about uh, RMS current. Okay, RMS values of the phasors. RMS values. RMS values means root mean a square. RMS means root means a square. Okay. So what we do? We first find the mean of a square, then take the root. Okay. So how to get mean of a square of a function? RMS value of fx. How to get RMS value of fx? It is a function of x, so we square it. No, we square the function, then integrate, and we are trying to find it between two limits. Okay, this is the mean of a square. This is mean of a square. If you take the root, it will become root of mean of a square. Okay, root of mean of a square. So suppose we have a current I is equal to I naught sine omega t, and we have to find its RMS value. So what we are going to do? What we are going to do? IRMS will be as first square it. So both things we will get squared. Then find the average, and RMS value we are going to find between in within a time period, within one time period. Okay, so I will do it from 0 to t. I will do it from 0 to t. So this is a square of mean of a squares. Okay, if you take the square root, you will get the RMS value. You will get the RMS value. So what we are going to get? I naught you can take out. Okay, I naught you can take out. Okay, and we are going to find the RMS value of this thing, sine square omega t dt divided by dt 0 to t 0 to t, and this thing. Okay, RMS value of sine square, RMS value of sine function over a period of time will be 1 by root 2. Okay, so I will do this calculation. Okay, I note is there. I will do this calculation in the next page. Okay, in the next page, what I want to do, sine square omega t dt 0 to 1 time period divided by dt 0 to 1 time period, then we are taking a square root. So here what we are going to do, I will make it 1 minus cos 2 omega t dt, and this is okay, sine square omega t is what, 1 minus cos 2 omega t divided by 2, and then we are going to do the integration. Okay, and then we are going to divide by dt 0 to t 0 to t, and then we are going to take a square root. Okay, so what we are going to get, 1 by 2 dt 0 to t divided by divided by just t, okay, under root minus cos 2 omega t dt divided by 2 divided by t. Now this part will give you half, and this part will give you 0. This part will give you half 1 by 2, and this part will give you 0. I am writing this thing. I am writing these things directly. You check the result, okay? No worries. And what is t? Remember this value. Omega t is 2 pi. Omega t is 2 pi. And 2 omega t will be obviously 4 pi. You will get sine omega t divided by 2, okay? And upper limit will be 0. So upper limit will be 4 pi. Lower limit will be t, and lower limit will be 0. In both cases you will get 0, okay? So what I got, IRMS will be, I will write it here. This part you will get I naught by root 2. IRMS, okay? And this result is true. This result is true. And this result is true for any other phasor also, okay? Suppose this is EMF, right? And there can be some other angle phi naught. Here also ERMS will be, E naught by 2 or root 2. Okay, so what is the significance of RMS value? We will talk this thing only in case of resistive circuit. We will see that RMS value is the current. Okay, RMS value of current will be equal to the DC current, which will give us same heating effect, okay? RMS value will be the DC current which will give us same heating current, okay? Now we will do one AC circuit, okay? AC circuit which is purely resistive, and we will see how much heat is being produced, okay? Then we will understand the significance of RMS value. So we are going to discuss different AC circuits, okay? Simplest of them is purely resistive circuit, okay? Purely resistive circuit is what? This is the simplest, okay? So what we have a resistance, and we have a source of EMF. Source of EMF, I am showing it, E naught sine omega t. And what we have to find? I. We have a resistance R. So using the Kirchhoff law, you can write E minus, the applied voltage is E naught sine omega t, and the current is I, and this gives us I is equal to E naught by R sine omega t, and I will write it I naught sine omega t. So EMF was E naught sine omega t, right? And current is I naught sine omega t. you can see that there is no phase difference. Okay, here also omega t plus 0, omega t plus 0, there is no phase difference. So what can we say? Current and EMF both are in phase, both are in exactly in phase, there is no phase difference. Okay, so what does it mean? What does it mean? It means that they will follow cycle, they will start from zero simultaneously, they will reach the maximum value simultaneously, they will reach the minimum value simultaneously, this thing. Okay, so this is one of the axis and this is our time axis. And first I will draw E naught sin omega t in the with the help of white one. Okay, so this is E and I both. So first I am drawing E. So here I have shown you two cycles. Okay, cycle starts from 0, this is start from 0, this is one time period, and this see here two cycles are completed. Okay, so this is EMF. I will show you E naught sin omega t, right? And let us say this resistance is half unit. Okay, if this resistance is half unit, then current will be, this current I naught will be double of E naught. So the graph will look like this. Okay, I will show it in some other color, blue. So this will look like this. What you can see here, current current is double because resistance was 0.5 unit. Okay, but what you can see there, current and EMF both are in sync, both are in phase. That means both are starting from 0 simultaneously, they are reaching the peak values simultaneously, they are again going to be 0 simultaneously, they are reaching the minimum values simultaneously. You can see that they are completing everything, they are doing everything simultaneously, right, side by side. So this is the meaning of being in the phase, this is the meaning of being in the phase. Okay, now I will we are going to discuss power dissipation in purely resistive circuit. So power dissipation in purely resistive circuit. Power dissipation in purely resistive circuit. So how to get power? Power will be EMF square by R, right? So E naught sin omega t, we have to square it. So this is the, we are trying to find average power. Okay, average, I will write the average here also. So this is the total power in one time period. If you divide by the time, we will get the average power. Once again you can see that This is the same thing we have done. Okay, v square by r, right? We have to divide by r also. So what we are going to get, e square by r we are going to get, and we are going to get sine square omega t dt integration 0 to t divided by dt 0 to t. This thing we already have done. This calculation we have already done. This calculation with a square root was 1 by root 2, and without a square root will be half. Okay, so p average will be e naught square by r, and there is 2 also. So it will be e naught by root 2 the whole square divided by r, or you can also say that ERMS the whole square by r. Okay, so what you can see that if you use the DC current, E DC the whole square by r. If you use the DC current, then EMF should be equal to ERMS. Okay, EMF should be ERMS, or in other words E naught by root 2. Okay, so that is what we have. So basically it is the effective value of the EMF. Similarly, IRMS is the effective value of the AC current. Okay, in purely resistive circuit. Okay, now we have to understand something. We are doing some calculation again and again, so we need to avoid this. Okay, average value of sine square omega t, this thing is called average value of sine square omega t. This will be 1 by root 2. Okay, and if you take the square root, so basically this is the RMS value of sine omega t. This will be 1 by root 2. Okay, and average value of sine omega t is 0. Now it is not always true. We are talking about one time period. In complete cycle, in a complete cycle. In a complete cycle, you need to understand all these things. Okay, this will be useful. Okay, now what about AC plus DC mixture? Okay, the current can be RMS value in case of AC plus DC. So suppose the current is A plus B sine omega t. What will happen in this case? RMS value. So this A is constant, this is a AC part, and this B sine omega t, this is the DC part. Okay, and we have to find the RMS current. So what we are going to do, again the similar thing we have to do. We have to square it. We have to square it so that we can find the average value of this thing. Okay, we just found the average value of this thing, and then we have to take the a square root. Limit of integration is one time period. Okay, one time period. So this will be a square dt 0 to t divided by dt 0 to t. Okay, okay, looks like I should not have written this thing here because the space is low. Enough space is not there. No problem. So this will be a square dt integration 0 to t divided by dt 0 to t. Okay, this is the first term. Second term will be b square sine square omega t dt 0 to t then dt 0 to t, and third term will be 2ab sine omega t dt 0 to t divided by dt 0 to t. So this looks like a long thing, but good news, this will simply become a square, right? This will simply become a square. IRMS will, this will simply, first term will become a square and this term will be b square by 2. See, sine square omega t dt divided by dt integration 0 to t, we found that this value will be 2. So you will get this calculation, you have to do once. Okay, okay, and this part's average value of sine omega t over a time period, it is 0. So this part is going to be 0. So IRMS is going to be a square plus b square by 2 under root. So if you have two things, AC and DC, then you have to AC part you just have to square. Okay, but what you have to square for DC part you have to just square. Okay, but for the AC part you have to square the RMS value. RMS value will be b by root 2, a square will be b square by 2. Then you add them and take the square root. Okay, so this is how we get the RMS value of AC plus DC. For example, suppose the current is 5 ampere plus 10 ampere sine omega t plus pi by 2, and suppose someone asks you the RMS value, then what you have to do? DC part just a square, but this you have to square and divide by 2. So RMS value is squared, and then you add them and it will become root 75 or 5 root 3 ampere. So this is the RMS value when the things are mixed. Okay, okay, good. Now the next thing we are going to do, we will talk about purely capacitive circuit. Okay, so how the purely capacitive circuit, we will do it in the next page. Okay, we will do it in the next page. Purely capacitive circuit. So in purely capacitive circuit we have a capacitor and we have a source of EMF. This thing means AC source. Okay, An EMF source is E naught sine omega t, and that's it. And capacitance is C. Let us say some current is going. We don't know this current, okay? We have to find the equation of this current, okay? Capacitance is C and charge is Q here and minus Q here. So we will apply the Kirchhoff's law. Kirchhoff's law is what? This is the applied voltage, this is the source, okay, which is being applied to the, and this is the voltage drop there. So from here Q will become C E naught C sine omega t. So here charge, see here, here EMF is also sine omega t, charge is also sine omega t. So charge and EMF both are in phase. But what about current? Let us see. Current I will be dq by dt, and we will see that sometimes we write minus dq by dt, sometimes we write plus dq by dt. The reason is that here if current is going this way, if the current is going this way, uh, charge will increase, okay? So plus dq by dt. If current is going this way, charge will increase, so plus dc by dt, dq by dt. So if you differentiate it, E naught c will be there. Differentiation of, if you differentiate it, differentiation of sine omega t will give you omega cos omega t. Now this is the change, okay? So EMF was sine omega t, charge was also in sine omega t, but the current is in cos omega t. So it looks like EMF and current both have a phase difference, right? And I would like to write this way: E naught 1 by omega c and sine omega t plus pi by 2. So what is noticeable? Noticeable thing is that this is still sinusoidal function, but this is ahead by an angle pi by 2. Current is ahead of EMF by an angle pi by 2. I will show it in the graph also, but right now you can see that current is ahead, current is leading, voltage is lagging by pi by 2. And what about this part? This thing I is equal to V by R, right? This thing has units of resistance, but it is not called resistance, it is called reactance. I will explain this thing also. So xc is 1 by omega c, we call it capacitive reactance, and it looks like resistance, okay? It works like resistance, okay? So basically when resistance is high, current is low, right? When resistance is high, current is low. When the current will be high, if omega is large, current will be reactance will be large. So if omega is large, you can see that current will take, EMF will take good amount of time, large amount of time to reach the maximum, then large amount of time to reach at zero again, then again large amount of time to reach the negative value again, and then again zero, okay? So if omega is if omega is a small, time period is high, okay? So you can see that charge flow will be slower, it will be charged, but after a long time, okay? It will get discharged, but it will take a long time. So you can see that if omega is large, xc, sorry, if omega is small, xc will be large, resistance will be large. Now what about C? For a given voltage, if C is small, it will get its maximum charge will also be small, right? So maximum charge is a small, so overall charge flow in positive half cycle will be a small, overall charge flow in the negative half cycle will also be a small. That means current will be a small, that means resistance will be large. So omega, if the omega is a small, C is a small, current will be, resistance will be large, okay, and current will be a small. That is the meaning of capacitive reactance, okay. So this part we explained. Now why are we getting this pi by 2, right? So voltage and charge, voltage, voltage was sin omega t, charge was also sin omega t, but current was in cos. Let us see the graph, we will have a better idea, okay. So I will make the graph here. I will make the graph here. Okay, first graph I will write the EMF part. EMF is sine, so this was easy. Drawing sine function is, I find it easy, okay. So this is E naught sine omega t, okay, and other one, other one is cos omega t, right? So what for the sake of simplicity, for the sake of simplicity, let us see, let us say this xc value is 1. Suppose this value is 1, so numerical value of I and E will be same, right? So I want to keep the height same, okay, nothing else. So current will be something like this, okay. What you see here, this is I naught cos omega t, right? This will be I naught cos omega t. And I will erase this part, okay. So what you see here, cos graph is leading, okay. When sine is 0, cos is already at the peak, okay. So it is leading, okay. It is leading by 90 degree. But you can see that both graph look similar, both are following each other, okay. Uh, okay, both are following each other. What you see here, when the when EMF was 0, when EMF was 0, current charge will also be 0, but current is highest. Current is highest how? See, see, if EMF is, if sine omega t is 0, EMF is 0, charge is also 0, but rate of change in charge is not 0, it is maximum. When sine is 0, its rate of change is highest, and rate of change in charge will give us current. So current is highest. So you can see the reason behind the lead, okay. When EMF is 0, current is highest, okay. And here you can see that EMF is highest, so EMF is highest, so the charge across the capacitor is also highest, but the charge is not changing, it is not charging or discharging, so current is zero. Okay, this way you can explain uh, everything. Okay, so it looks like we understood purely capacitive circuit, purely a resistive circuit. Okay, purely resistive circuit, and then our attention will be purely inductive circuit. Okay, purely inductive circuit. In this circuit we have a inductor, just inductor, and we have a source of EMF. Okay, source of EMF. Okay, now this thing can be explained using two ways, but let us go for the old way, then we will talk about new way also. Suppose EMF is E naught sine omega t, and current is I, we don't know this I, and here EMF will be minus L di by dt, we know this thing, right? EMF across the inductor will be minus L di by dt. Now okay, let us do it. We are going to use Kirchhoff law. E naught sine omega t minus L di by dt is 0. So what will be I? Di will be E naught by L sine omega t dt. Okay, so this integration will come in I is equal to E naught by omega L integrates omega, because when we integrate this thing, we will get cos omega t, but we have to divide by omega because it is the coefficient of t. Apart from that, I will write one constant also. Okay, so this is a indefinite integral, so I will write a constant also. Okay, in the first video what we have done, we have shown that these phasors will have average value 0. We have started from flux also. Flux was sinusoidally changing. Total change in flux in one time period 0. Total charge flow was also 0. Average value of current was also 0. Average value of EMF was also 0. Okay. So in AC, in purely AC, I am not saying there is no DC component. Okay, in purely AC, what will happen? Net charge flow over n number of cycle, it will be 0. So this C must be 0. Okay, this C must be 0 because total charge flow is obviously 0. So we are going to say this is 0. Now I'm doing some mistake. We have a minus here. Okay, we have a minus here, so I will be E naught by WL, and I will write this way: sine omega t minus pi by 2. Here in the previous one what we got, current was leading. In capacitance current was leading, here current is lagging, so we will do one what, we will make a graph and we will try to understand why. Okay, we will make a graph, we will try to understand why. But first of all, let us discuss about this omega L. Omega L is called inductive reactance. Inductive reactance. If omega value is large, inductive reactance will be large. I mean, if the fluctuation is large, what will happen? You know that if the rate of change in current is high, the inductance will be more effective, right? And if the inductance, see, if omega is 0, it is just like DC, okay? And this wire will allow good amount of current, okay? And if this is not a inductor, just a wire, again current will be high. So if omega is 0 or L is 0, close to 0, inductive reactance will also be very close to 0, okay? So you will get a very high value of current. It will be like a circuit of zero resistance. Current will be very high. But if omega is large, L is large, it will impede the fluctuation of current, okay? And what will happen? You will get a small value of current. Now we will try to discuss this part, okay? We will try to discuss this part. For that we need to make a graph, and graph will be something like this, okay? This is T and this is, first I will draw EMF, okay? EMF I will draw by, so EMF is simple sine curve, okay? Does it look good? No. Okay, yes. So that is EMF, that is EMF E naught sine omega t, and that I will write I naught sine omega t minus pi by 2. So this is lagging, okay? This is lagging. I will draw this lagging part here in red, okay? So it will look like this. It will look similar. Mm-mm. Yeah. So current is lagging, okay? uh, EMF is 0 but current is negative maximum. Here current is lagging by 90 degree, okay? After some time current is becoming 0. Current is taking some time to reach at 0 while EMF was already 0, okay? So current is lagging. uh, that is the meaning of that part. So I will what I will do, I will just show what we have done about lagging or leading part, okay? So uh, circuit circuit type circuit type EMF, current, okay? Circuit type means purely resistive, okay? EMF we take AMF E naught sine omega t. Current came to be I naught sine omega t, okay? Lag or lead, no lag or lead. So Here EMF and current, they are in same phase, okay. And inductive, no, capacitive, okay. We can write inductive first also. Capacitive, uh, purely capacitive. Here it was E naught sine omega t, but it was E naught by I naught sine omega t plus pi by 2. Current leads the voltage. Current leads the voltage. In other word, voltage lags the current by pi by 2. Purely inductive. In purely inductive, it was E naught sine omega t, but this one was I naught sine omega t minus pi by 2. Current lags. Current lags the EMF by pi by 2. Okay, so I naught E naught by R, it is for resistive circuit, okay. And I naught is E naught by 1 by XC, sorry, 1 by omega C. This is for capacitive, okay. C for capacitive, and I naught E naught by omega L for inductive, okay. Okay, now what we are going to do, we are going to see one okay, we are going to do this thing purely inductive. We will use some other method also, okay. We use what okay, let us see what we did here in inductive circuit. What we did here, we used E naught sine omega t, okay. The voltage source was known, but current source was, we found this, okay, right. Instead of doing this thing, what I will do, I will say that we know the current, okay. I will say that I know the current I naught sine omega t, and we don't know the voltage, okay. We have already done this thing. We will do this thing. We will see the result again, okay. So applied voltage is E, we don't know the value, and applied current is this thing, okay. And this will be L di by dt. I is already known, okay. We already know the I, okay. So E will be minus plus L di by dt. L di by dt I naught we are trying to differentiate this thing. This time we are using differentiation. So differentiation of this will give you I naught and omega cos omega t. We can also write E is equal to uh, I naught omega L cos omega t. I will write sin omega t plus pi by 2. Now let us see what happened. This time current was known, we found the EMF. Okay, we found the applied EMF. Okay, results are similar. What we see, this still acts like resistance. Okay, and its name is inductive reactance. Inductive reactance omega L. But we are seeing what, there is a lead. So who is leading? Voltage is leading. In Okay, I will write both things. Okay, if E was E naught sin omega t, then I was E naught by omega L sin omega t minus pi by 2. So this was the result, right? I hope it is visible. If I is equal to I naught sin omega t, then EMF was I naught omega L, I naught omega L sin omega t plus omega t plus pi by 2. Okay, let us see here. Voltage is known, and what we see, current is lagging. Current is lagging. Inductive reactance is still omega L. Current is known, and what we saw, voltage is leading. See, voltage leading means current lagging. Current lagging means voltage leading. So both things are leading, leading or lagging part. It is same thing. Okay, and we are getting the inductive reactance same. Okay. So I hope this part is clear. Now what we are going to do, we are going to do LCR circuit. Okay, LCR circuit, and let me see how much time we have. Okay, so it is already 53 minutes. Okay, now LCR circuit. So in LCR circuit, what we are going to do, all components will be there. LCR series circuit. Okay, I will say it, LCR series circuit. LCR series circuit. Okay, so what we have here, we have a resistor. Okay, and we have a inductor. We have a resistor, we have an inductor, and we have a capacitance also, and we have some source of EMF. Okay, and E naught, E we don't know. Okay, I am using what I am using here, I know the current. Okay, what I know here, I know the current. Okay, why I am using this, because this is a series circuit, everything will be same. Okay, in resistance also current will be same. Okay, in inductance also current will be the same, and voltage will be IR, right? And here voltage will, okay, voltage will decrease. Okay, and here voltage will be minus L di by dt, and here voltage will be, what will be voltage? Q by C, right? Q by C. Okay, so let us do this thing. Okay, here voltage will be minus Q by C. I am assuming that this is plus Q and this is minus Q. So this is our source EMF. We are going to find its value. Okay, so obviously we are going to take it positive. Okay, this EMF we don't know. Okay, and this will be minus IR, and this is minus L di by dt. This is minus Q by C, that is 0. Okay, so EMF will be IR plus L di by dt plus Q by C. Okay, instead of Q by C, I would like to write integration I dt by C. Okay, instead of Q, I have written what? Integration I dt by C. So this EMF is I naught sine omega t. Okay, R I am writing here. Okay, and L di by dt. Okay, so if you differentiate this, you will get I naught omega. Differentiation of this will be I naught omega cos omega t. So omega I naught cos omega t differentiation. Okay, and now we have to integrate. Here we are differentiating I, here we are integrating I. So this will again be cos, but it will be minus cos. When you integrate sine, we got minus cos. So what we are getting? Minus, okay, again, this is I naught is there, C is there, and we will get cos omega t, and omega will be divided. Okay, once again I am not writing the constant part. Okay, once again I am not writing the constant part. Okay, because in the long run, not in the long run, in a complete cycle, average EMF should be 0, and that is only possible when the constant part is 0. Okay, average value of this thing in one time period is 0. Average value of cos is also 0 in one time period. So, and yeah, we talked about this. This will be minus. Okay, minus. So what EMF we are getting? I naught is everywhere, right? I naught is everywhere, and we are getting R sine omega t plus WL minus 1 by WC cos omega t. WL minus WT 1 cos omega t, and I naught is multiplied everywhere. Now this thing, it looks familiar. Okay, why does it look familiar? We can use the use our phasor analysis. Okay, we can use our phasor analysis. This cos omega t means 90 degree ahead. Okay, 90 degree ahead. So I will write it again. I naught r sine omega t plus wl minus 1 by wc sine omega t plus pi by 2. Okay, here instead of cos omega t I have written what? Sine omega t plus pi by 2, because sine omega t plus pi by 2 is cos. So we have two phasors. We have two phasors, and one is leading by angle 90 degree. One is leading by angle 90 degree. So I will try to make it clear what is happening. This is our reference axis, okay, and this is perpendicular to the reference axis. This is perpendicular to the reference axis, okay, and current phasor is I am showing current phasor with the red one, okay. So this was our current phasor in the red. Okay, let us make it large, okay, no problem. This was I naught sine omega t, okay, and the voltage phasor, has three parts, okay. First part was voltage across the resistance, right? Voltage across the resistance was I naught r. Voltage across the resistance was I naught r sine omega t. So what is happening? I will call it VR, okay. I will call it VR. This is the voltage across the resistance. It is in phase with the current, okay, and voltage. But we have seen that voltage across, okay, voltage across the inductance was 90 degree ahead, right? And VL was I naught omega L. Okay, it was 90 degree ahead. That means V naught. Okay, this was the value, right? Sine omega t plus pi by 2, right? Sine omega t plus pi by 2, and it was actually we got cos, right? But cos omega t, that is the same thing, okay. And what was wc? I will show it in other color, blue. And vc was I naught by omega l. I naught by omega l. This was minus cos omega t. This was what? Minus cos omega t. But instead of minus cos omega t, I will write sine omega t plus pi by 2 with a minus sign. Okay. We have a different way to write, okay. Okay, if you don't want to write minus sign, you will write this thing. Okay, I will write both thing. Okay, I will try to explain what we did. VC value we was I naught by omega c cos cos omega t with a minus sign. Okay, you can see here we got cos omega t but with a minus sign. Okay, just opposite of this thing. It means that voltage across the capacitance and inductance, they are opposite, 190 degree ahead, 190 degree apart. And the same thing I wrote this way, I naught by wc, we can write this way also, sine omega t minus pi by 2. So I will explain again because this is complex and people get confused. Okay, this is the voltage phasor. Okay, this is the voltage phasor, and voltage across the resistance is in the same direction. I will not say same direction, same phase, both are sine, but voltage across the inductor is 90 degree ahead, and voltage across the capacitor is 90 degree lagging. Okay, voltage across the capacitor is lagging compared to the current. Now these two things are opposite because you can see that minus sign. When both are cos, we get the minus sign. I naught omega L. If you write cos omega t, see both is cos omega t, but there is a minus here, so just opposite. Okay, just like vectors, when there is a minus sign, we say that they are opposite. Okay, so this will go like this. This will become, this will go like this will go like this way. Okay, this will be I naught r sine omega t, and this will be I naught omega l minus 1 by omega c cos omega t, and the resultant will be resultant we can find this way. Resultant we can find this way. This is the resultant. Okay, so resultant will be uh, emf. Resultant will be I naught r square. Okay, sorry. Okay, this thing I will write in the next page. Okay, because you can see that we have less space. So what we discussed so far, what we discussed so far, uh, this was the voltage across uh, this was the voltage across resistance, and this was voltage across resistance plus capacitance, resistance plus capacitance. Okay, and resultant will be found like this. Okay, and the resultant will be this. Okay, this will be v, this will be total EMF. This will be I naught, I am keeping alone, R square plus omega L minus 1 by omega C, the whole square, under root sine omega t plus alpha. How can we get alpha? This angle is alpha, right? We have discussed this thing in phasor diagram, first video. So this tan alpha is given by this value. Tan alpha is omega L minus omega C, 1 by omega C divided by R. Now let us discuss this part, okay? If omega L greater than 1 by omega C or XL greater than XC, if inductive reactance is higher, then tan alpha will be positive. Tan alpha will be positive. Alpha greater than 0, okay, voltage will lead the current, and opposite thing is also true. If XC is larger, voltage will lag, okay. If XL less than XC, current will lead. If XL is equal to XC, that means WL is equal to 1 by WC, and W is 1, omega is 1 by root LC. Okay, here no lag, no lead, okay, no lag, no lead, okay. This is a special case, and this is the case of resonance. We will discuss it later. I am going to end this thing right now, okay. Thank you everybody.